All right. We are recording this session, so I didn't forget that. How are you doing, guys, this morning? Can you hear me?
Yes.
Good morning. It's Wednesday, November 18th. So we have just a few days before the Thanksgiving break. And just a few more lectures to go through and a few tests, right? So you saw that I gave you some extra credits, things to do, right? So I don't know if there's any special preparation that is required for it. It's something that you already know since you took the exams. And the questions are quite simple. So you may want to brush up on some of the slides, for example, if you want, but depends how you feel. If you feel that you did well on the tests, if you don't need anything special, just go ahead and take it. If you feel like you didn't do well on the tests, maybe some reviewing of the slides could be helpful. So I will also schedule a final exam review. So we'll have that. That will be after exam 3. I will send out the time. That is hopefully that will work for everybody. If not, again, we'll record it. And is there anything else? Any other questions you have?
So the extra credit test, that's closed note. You can't have open notes during that.
No, why would it be open notes?
I don't know. You never know.
No, it's the same as it's just imagine these questions would be on the actual tests, right? So it's the same format. Everything is the same. Just an opportunity to earn some extra points and give you some more courage to finish the semester and get ready for the final. Remember, final is very important because it counts for as 2 exams, really, because you get the grade in the final and hopefully you studied hard and you can drop one of your other exams and we're going to replace it with the grade you get in the final. So final could be could have a big impact on your grade. All right. So we still have some slides to go through from lecture 11. And then we'll start on the last lecture, lecture 12. So for lecture 11.
Sorry, Dr. Korniak, go ahead. One quick question.
Yeah.
So for the extra credit, is that from all of our previous past tests or just from the last one? Or does it also include content from exam 1?
Yeah, no, it's over everything we've studied so far.
Okay.
Even the exam 3, which hasn't happened yet, but the material, we already covered it. So there's not much from the last one, but it's only 10 questions. So it's all right. So and plus things like that, like for example, this alpha helix, right? You already seen it. You already know most about it. So I don't really think you need to study that in great detail. Just review. All right. So we'll talk about glucose transporter as the next type of transport system. So glucose transporter is a part of the facilitated transport system. Facilitated. You guys remember what facilitated means?
It uses a protein and no ATP.
Right, so there's no input of energy, right? So what the transporter will do, it will provide a path. It will provide a path for a molecule to get into the cell, for example. But the molecule has to go into the cell using its own concentration gradient, right? So for example, glucose here, glucose transporter, glucose by itself is polar, right? So there are 6 hydroxy groups. So 6 or 5? 1, 2, 3, 4, 5, 6, right? No. 1,
5 in the ether.
3, 4, 5. 5 hydroxy groups. Yeah, correct. So 5 hydroxy groups. So obviously those, remember, those will form hydrogen bonds with water. And so glucose will be highly hydrated, and it's going to be hard for it to get into the cell. And so that's the function of glucose transporter, is to provide a path. And so the way this works, it's a protein, transmembrane protein. If you count these, there should be 12 transmembrane domains. But you can see here, most of these are yellow. Yellow are those amino acids which interact with the lipid bilayer, which allow for the transporter basically to localize in the lipid bilayer and not leave, right? But that's not going to be enough. You need to have hydrophilic residues, polar residues, or even charged residues. There are not too many charged inside the inside of the bilayer, red ones. Most of them are on the outside, but a lot of polar ones, a lot of blue ones. Oh, a bird just flew into my window. So, so these blue ones, they will provide the path for the glucose to come in to the cell. Now, there are actually a couple of such transporters, or there are a number of them. They all abbreviated as GLUTs, or some people say GLUTs. So there is a GLUT1, which is a very common one. So it's you can just, it's an abbreviation for glucose transporter, right? GLUT1. So this is present in the membranes of erythrocytes. It's also present in the blood-brain barrier, BBB, right? So remember, glucose is the only source of food for the brain, and so the brain has to receive a lot of glucose, but again, it's not going to be able to cross the blood-brain barrier by itself. It needs to have glucose transporters. So, so these polar residues, what will happen, remember, in the alpha helix, so this alpha helix is known as amphipathic. And why is it amphipathic? Is because one side of it is hydrophilic, the other side of it is hydrophobic. So you can see the way, remember, one complete helical turn is about 3.6 amino acids, right? 3.6 amino acids. And so you can see every 34th amino acid will be polar: asparagine, threonine, serine, right? And every 3 or 4 on the other side will be non-polar: leucine, phenylalanine, valine, isoleucine. And so what happens here is that when you have a helix like this, the polar residue will occupy the will arrange themselves in such a way that they will coordinate with the other polar residues from a different helix or helical segment to basically create a sort of a channel, a polar channel for glucose to pass through. And on the outside, you will have non-polar portions, which will anchor this whole thing in the bilayer membrane, right? So the outside is non-polar for the interaction with the lipid tails, and inside it's going to be polar for the glucose to pass through. Now there is this kind of half of this has been cut off of the glucose transporter. You can see there is a central cavity here. So glucose kind of well, the inside, it comes out actually, right? It comes in somewhere here and comes out somewhere there. All right, so all these details are could be useful, but what I want you to remember is amphipathic helix, and also obviously I want you to know how this works. And it's a pretty simple cartoon. So glucose, so there's an opening on the outside when nothing is bound. The opening on the outside of the membrane is waiting for the glucose to come in, right? Sort of kind of T1 state. So glucose binds to this T1 state. Once the glucose has bound, then there's a conformational change in the transporter so that the inside part opens up and allows for the glucose to come out on the other side. So pretty straightforward. So there are one binding, conformational change, departure, conformational change. So 4 steps, very simple mechanism of action. No energy is required because it's driven by the concentration gradient, right? So here we have high glucose, and here we have low glucose. And it's controlled by the concentration gradient, right? So if the brain is really starving for glucose, obviously the concentration of glucose on the outside will be much higher than on the inside, and the transporter will transport many more glucose molecules because of the high concentration gradient. All right. So that's, I think, all I want to say about the glucose transporter. Now let's look at bicarbonate transporter. We're just going to look at some examples of these of these transport systems, just to for you to appreciate their functional significance. So here, bicarbonate transporter. Now, basically, what it allows one to do, it allows one to, for example, to remove carbon dioxide from the respiring tissues and release it in the lungs and be exhaled, right? So carbon dioxide by itself is poorly soluble in water. Remember carbon dioxide. Does carbon dioxide have a dipole? What you remember from general chemistry? Is there a dipole?
No.
No. So this is the central carbon, right? Central carbon. And it's sp hybridized. Sp hybridized, which means it's linear. It's 180 degrees. 180. which means that it has zero dipole. So carbon dioxide is poorly soluble, and so bicarbonate transporter system using erythrocytes facilitates the removal of carbon dioxide. And so what happens here, so on top we have respiring tissues, on the bottom we have erythrocytes which are in the blood vessels in the lungs. And so the enzyme which is involved in this is known as carbonic anhydrase. And so carbon dioxide diffuses into erythrocyte as a gas, right? So easily crosses cell membrane. It's nonpolar. And here the carbonic anhydrase will catalyze a reaction between carbon dioxide and water and produce, now first this reaction produces, let me write this down, you probably remember from general chemistry. First, this reaction produces carbonic acid, H2CO3, right? Which then dissociates into H plus and HCO3 minus. H3O3 minus, which is what's shown here, right? And so, so this is a an antiport system. So in the respiring tissue, it's based on hold on a second. All right, and so this, and now this bicarbonate, right? So now it's polar, it can go out. It's an antiport system, and the chloride will come in. The chloride will come in, and this will now dissolve in blood plasma. So carbon dioxide was not dissolving, and now this will dissolve in blood plasma. And then the blood plasma will deliver it to the lungs. And what happens to the lungs? The bicarbonate then will enter the erythrocyte in the site of the lungs. Again, it's an antiport, and the chloride will come out. The chloride will come out, and so the bicarbonate will then be converted back to carbon dioxide, which will be exhaled in the lungs, right? Because as we exhale, the concentration of carbon dioxide drops in the lungs, and it will force the carbon dioxide to come out, and it will force the whole entire equilibrium to go out. Now, tell me something. Tell me something. Why do we need the chloride? What does the chloride do? It's not an active transport. It's a facilitated antiporter, facilitated transport system.
It's maintaining the charge in the tissues, so we're losing a negative ion, so we're keeping entering a new negative ion.
Perfect, perfect. Yeah, that's my explanation as well. It maintains the charge neutrality inside the erythrocyte and outside, right? So the negative charge comes out, another negative charge comes in. Same thing here. Yeah, good job. All right, any questions? Okay. Now there's another type of glucose transporter, which is now is a sodium glucose symporter. Sodium glucose symporter. And so this system is involved in the absorption of glucose from the digestive tract, right? So this is going to be intestinal epithelial cells. Intestinal epithelial cells, you can see, so this is intestinal lumen, all right? This is where the food is. Now you can see there's what's known as apical surface, where we see these microvilli. Microvilli, basically, you can see these what's the point of having these microvilli in the intestinal epithelial cells? What do microvilli do?
They increase the surface area.
Yeah, just the surface area, so that there is more. You can put a lot more of these various transport systems into the membrane to allow for the nutrients to cross from the intestinal lumen into the bloodstream. And so here, so this is 2 sodium ions and glucose will come in, right? And so, and it's driven by the high extracellular sodium. In general, it's important to know that if you have a cell, right? If you have a cell, like so, then sodium potassium, there is a sodium potassium ATPase, which you will study in great detail in Biochem 2 in metabolism. But in general, in a cytosol, so sodium concentration is 12 millimoles. Now I need a bigger picture actually. 12 millimoles, and potassium 140. Millimoles. Now on the outside, it's reversed. So potassium is Potassium is 4 millimoles. And sodium 145. Millimoles. And this is achieved due to this ion pump known as ATPase. So what it does, it uses the energy of ATP to pump sodium out of the cell. You can see 3 sodium ions get out of the cell and 2 potassium ions come into the cell. And because of this is highly active, widely spread on most cells, these concentrations are typical for in a biological system in an organism. And so so once the glucose comes in, right? Once the glucose comes in, it will because now its concentration building up inside the epithelial cell, and it exceeds, at some point starts to exceed the concentration of glucose in the blood. It will just simply come out using the GLUT2 now. Glucose transporter 2, right? We talked about GLUT1. So this is GLUT2, facilitates downhill efflux. So efflux meaning movement outside, export. So, what happens to sodium? So to make sure this continues to work, the sodium has to be removed. The sodium has to be removed, and that's the function of the ATPase, sodium, potassium, ATPase. As you remove sodium, then more sodium will come in. So the glucose basically is driven by the concentration of sodium, right? So it comes in together with sodium because the concentration of sodium is low due to the ATPase. Does it make sense? So it's very, I think it's a very beautiful system, the way it works. Basically all down concentration gradients, right? So if you don't have the concentration gradient for glucose, right? You utilize that for another molecular ion. So through the Symport mechanism. So this is sodium glucose Symporter. All right. So let's talk about active transport. So those were examples of passive transport, but facilitated. And now there are examples. These are examples of active transport where energy is consumed. And so in many cases, these will be ATPases. ATPases are basically enzymes which utilize the energy of ATP to allow passage of ions and molecules across the cell membrane. So remember, there's a lot of energy in the phosphoester, right? So once you cleave one phosphate off, you generate energy. So this is primary active transport, where you cleave one ATP and the molecule of interest will just simply come out, right? So the substrate, and it's driven by the energy of ATP hydrolysis. And so here, this is secondary active transport, which is again, the energy is coupled to concentration gradient of another molecule. So you can see here, S1 this is something else, some other molecule, right? Which will be pumped out of the cell using ATP, ADP, pumped out of the cell. To leave the cell, and you can see here now its concentration building up on the outside, and it reduces, gets smaller on the inside, and then it comes in together with the substrate of interest, comes together inside the cell through a Symport mechanism. Now, what does this remind you of? Does this remind you of anything? The secondary active transport, based on what we just talked about?
The glucose transport.
And that's interesting. Yeah, glucose transport. So it's kind of similar, I would say. So in the text, this is kind of treated as a just simply facilitated transport, because glucose and sodium come in as a simple in a Symport mechanism, but then sodium is pumped out, right? So the only difference is that sodium ends up in the bloodstream, whereas this sodium comes with food. But that's the only difference. But in many ways, you can treat this as a secondary active transport system, right? Because you do have ATPase, so energy which is applied to a different molecule, sodium.
I was always taught that this mechanism was a secondary active transport because it basically the sodium potassium pump is what creates a concentration gradient that allows the sodium
Yeah.
glucose pump to work.
Yeah, so maybe that slide does need to be, well, that's how it's discussed in the book, in a textbook. But maybe this should be moved into the secondary active transport category. Yeah. Well, I mean, labeling, you can see there are a lot of gray area here. Labeling, it's good to know the categories. It's just for us to organize information, but you can see there's a lot of gray area between different mechanisms. So once you know these examples, you know how they work. Categorizing these is not really something that you're going to be doing. Okay, so another system which utilizes ATP hydrolysis to drive transport of substrates. Now these are ABC transporters, very prevalent in many different cell types. Basically, they have many different functions. Basically, they serve as a way to get rid of different cellular waste and toxic molecules, right? Toxic molecules from the cell. They consist of this transmembrane domain. There are actually two homologous transmembrane domains in the blue, dark blue, and light blue color. And there are also two nucleotide binding domains. That's where ATP will bind, which is in the cytoplasmic surface. And then obviously there's a cavity here inside, which will allow for the molecules to come out. Now this is a similar one, which is now this is eukaryotic ABC transporter. Now this also there's a different word for it, ABC transporter, but in primary literature, oftentimes you see the term P-glycoprotein. P-glycoprotein. And this is just a homologous one, but present in bacteria. Also have a very similar structure. Now do we have? Yeah, we have slide how it works. Yeah, let's look at the slide how it works, and then we'll go back. I'll give you some information on P-glycoprotein. So the way this works is so the outside part of the ABC transporter is open, allowing for the substrate to come in, and the ATPs. So there are two ATP molecules. So there are two nucleotide binding domains. So two ATP molecules are sitting and waiting for their turn to be hydrolyzed. So once the substrate comes in, right, there's a conformational change which will cause the ATP to undergo hydrolysis to ADP, right? So adenosine diphosphate. So once that happens, then the nucleotide binding domains separate, allowing for the substrate to come in, for example. So these P-glycoprotein, even though they have a large number of functions so there are lots of actually different genes which encode for different types of these ABC transporters. They also kind of an Achilles heel of our ability to treat various health issues. So for example, in cancer, cancer cells hijack these ABC transporters and overexpress them on their surface and pump out the cancer drugs. So often referred to as MDR, multi-drug resistance. Multi-drug resistance. So many of these ABC transporters are specific for particular substrate, but many are not. In other words, they was known as a promiscuous pumps. And in which case it leads to a phenomenon of multi-drug resistance, in which it doesn't matter what drug you actually treat the patient with, it will be pumped out by the ABC transporter. So oftentimes what happens is, so the way this works is let's say a tumor is, the patient is diagnosed with cancer. And there's a tumor that can be excised and by surgery, radiation treatment, and then chemotherapy regimen allows one to get rid of the residual cells. So MRI shows no tumor. The patient goes home cancer-free, but then a year or 2 years later, a tumor comes back in the same area, right? And then the patient goes in for treatment. Exactly the same treatment is administered, but this time the tumor does not respond to the same drug. For example, one of the most common one, let's say doxorubicin. Doxorubicin. And so then the question is, okay, so the tumors have developed resistance to doxorubicin. Okay, then let's try a different drug. Let's try paclitaxel, which has a totally different mode of action, has totally different structure, right? So you would think that if the first time we treated the patient with doxorubicin, then the second time when we treat to paclitaxel, the cells should still respond. And what we learn is they don't respond. And so that's primarily due to the overexpression of these ABC transporters, which provide multi-drug resistance. So now it doesn't matter which drug you use, they will pump it out. They're promiscuous, they will just pump out any drug you administer. So there's been a lot of effort in pharmaceutical industry on developing drugs that can inhibit ABC transporters. So you may wonder, okay, why don't we just inhibit ABC transporter and co-administer this inhibitor together with a cancer drug? So this strategy has been pursued widely, but so far has not resulted in a clinically approved agent. And for some reason, these, I guess the physiological function of these ABC transporters is very important for normal cells, normal tissues as well. And so the ABC transporter inhibitors are just too toxic. It's too toxic and cannot be used to treat cancer because of this limitation. All right, do you have any questions, guys? So, all right. There is a sort of another, so this ABC type transporter, it's not really ABC transporter, is just the type because it's actually, it transports ions. It transports ions using the energy of ATP as well. And so the most known one is the one that actually has a defect. So there is obviously, you know, the disease cystic fibrosis, right? Cystic fibrosis, horrible disease, primarily, obviously, children suffer from it and usually don't live until into their adult years and die at the age of 15, 20. Now maybe 25 we have some better treatments, 25, 30, but they still cannot lead a normal long life. So so the way this works, so there is a chloride ion channel which is also coupled with the ATP hydrolysis for the transport of chloride. And so you can see what happens here is so this part is a regulatory system, so it's phosphorylated. So it's phosphorylated on serine. There are 2 nucleotide binding domains. So the channel is closed. It's R domain phosphorylated, no ATP bound. Then ATP comes in, binds. ATP comes in, binds, and the channel opens. The chloride is allowed to leave, right? Down the chloride is allowed to leave. And then ATP undergoes hydrolysis, goes into ADP, and this becomes dephosphorylated, and the channel is closed. And then the cycle will have to repeat itself again. Phosphorylation has to occur. Phosphorylation will lead to ATP binding chloride. The channel opens, ATP undergoes hydrolysis, which causes dephosphorylation, channel closes, and so on and so forth. So so there are basically three different states for this chloride channel. And so what happens, there is a mutation in this ion transporter in children with cystic fibrosis, which actually prevents this channel from working properly. Or in fact, I think this, no, I take it back. I think this mutation actually leads to the degradation of this channel. So you know that defective proteins are degraded in lysosome, for example, right? And so so our cells basically treat the mutated protein as a protein which is will not be functional and undergoes degradation. And what happens is, if there's no channel expressed on the surface of these epithelial cells in the lungs, right, then the chlorine is not does not leave the tissue into the lungs. If there's no chloride in the lungs, that means the mucus, there'll be a lot of mucus accumulation because the lungs will simply be dehydrated, right? And normally, if you allow for chloride to come into the lungs, then water will follow through osmosis, and the mucus can basically clear it. But if there's no chloride, there's no water, the mucus gets stuck in the lungs, which provides a breeding ground for various bacteria, right? Like Pseudomonas aeruginosa is one of the key ones that actually kills cystic fibrosis in patients. And it's just because the mucus cannot be cleared due to the absence of water and chloride. So yeah, things are taking longer than I expected. So why don't you actually read this by yourselves? Now, what do we have here? We have ATPases, which are proton-driven ATPases. Now, read page it's not very difficult. In fact, it's a pretty simple presentation. you will actually study this much more in metabolism class. Page 416. Page 416. Yeah, just page 416. I think that's all. They describe this in a textbook on page 416. Now for aquaporins, I don't know if there's a, you can look at those as well. You can look at aquaporins, page 423. 424. But the idea is that obviously water cannot cross cell membranes. It's too polar, right? And so aquaporins are channels which allow for the water to come into and out of the cell depending on the osmotic gradient, right? Osmotic pressure. So here we have a number of charged residues. So you can see here there's internal cavity. Kind of the molecules of water build kind of there's a line of them. There's a line of them. They basically just fill up this internal cavity coming from one side and are released on the other side. So there's a lot of amino acids which facilitate this kind of movement of water molecules. For example, this histidine here, you can see it's very close here, which plays a role in size restriction, right? So for example, molecules of water can pass through, but for example, urea, which is also a small molecule capable of hydrogen bonding, is slightly bigger. That cannot pass through. Two asparagines are also, what they allow to do is, so water dipole reorientation. So that is very important because now just think about it. If there's an alternative way for this to work is if the water molecules, for example, get stuck, and instead they will just start passing protons from one side to the other. So that's a possibility. So all the oxygens will remain in place and they will start exchanging their protons. So instead of a water channel, this will become a proton channel. So that obviously possibility has to be prevented. And so the water dipole reorientation basically makes sure that the proton hopping will not occur. Remember, it's called proton hopping. Now there's this arginine, which is positively charged. That makes sure that that hydronium ions don't get through, just neutral water, right? And so so water, now there's a it works with at a very fast rate. Hold on a second. Yeah, so this channel works at a rate of about 10 to the 9th molecules per second. So if you remember, for most enzymes, this was up to 10 to the 7th. So this is at least 2 orders of magnitude faster than any enzyme in the body, right? So aquaporins are some of the fastest macromolecules in a cell. All right, and the last one I wanted to show you. So this would be ion channel. Ion channel several transmembrane domains. This is potassium channel. Potassium channel, you can see here, the alpha helices arranged in such a way that there's internal cavity. And so here potassium arrives with its hydration shell, right? So hydration, the molecules of water are stripped off, potassiums get through, and the way they get through is by interacting with these carbonyls, right? So these alpha helices expose their carbonyl groups. And so obviously carbonyl will bind to potassium as a Lewis acid Lewis base interaction, right? And allow for the potassium then to get through and come out and regain its hydration shell. And so this is highly specific for potassium. So the carbonyl groups on the peptide chain actually control the size of ions that can get through. And potassium is obviously bigger than sodium, right? And so the size can be controlled by these carbonyl groups. So potassium will get through and sodium will not. All right, so what's left here is just a summary of various transport systems described in the textbook. Now, as you can see, most of these will be discussed actually later, right? Because for us, this was just an overview of different transport systems, but you will study these in much more detail in metabolism class. All right, you can go over the summary. Do you have any questions for chapter 11?
I have a quick question. It's not about chapter 11. It's about the extra credit. I remember you said like it's gonna cover all 3 exams. How much of chapter 12 will be on the extra credit, if at all?
12? We haven't started that yet, so there will be no chapter 12.
Okay, thank you.
All right, guys. We'll be talking to you on Friday. We will start chapter 12.
Thank you.
Yeah, bye-bye.